Now that we know a little bit about the requirements for a system to be in equilibrium, we have to learn how to study an equilibrium system. So using our traditional chemistry methods and look at like stoichiometric ratios, how can we calculate how much product is going to be produced from an equilibrium reaction. So we can't use the normal stoichiometric methods that we've learned up to this point. Because previously, when we did our stoichiometry, we would look at our reactants and we would know how much reactant we started with. Using the molar ratio, we could figure out how much product we should end with. But in the case of equilibrium, right, as the product is being formed, it starts reacting and going backwards, turning back into reactants. So we can't use traditional stoichiometry to figure out how much product we're going to form. That's where we come into a few special properties for equilibrium. So we're going to look at what's called the equilibrium constant, which we give the symbol Kc. Okay, you'll also sometimes see it written as Keq as well, which is also fine. That's a little more generic. So we're going to study our Kc. And Kc is a relationship between the concentration of products and reactants. So it's going to let us study how much at equilibrium, how many reactants do we have and how many products we have. So for a generic reaction, as shown, so we just have A, some amount of A plus B goes to some amount of C plus some amount of D, where the small letter is our coefficient and the capital letter is our element. We can write an equilibrium constant expression for this reaction. So we would write Kc is equal to the concentration of D raised to its coefficient, so D to the D, C to the C, over our reactants, and A to the A. So remember that these square brackets represent concentration. So when we're dealing with equilibriums, we do have to be working in units of concentration, which we can use as an aqueous solution, something dissolved, or we can look at gases as well. Okay, so what you see here is what we have is the concentration of products over the concentration of reactants. So Kc is giving us a ratio, this equilibrium constant. It's telling us when we're at equilibrium, how much products, the amount of products do we have compared to the amount of reactants. We'll study the value of it in a little bit, but there's a few conditions that have to be present, or a few conditions to know about Kc. One is that Kc is a fixed value at a specific temperature. So every reaction, every equilibrium reaction that exists has a specific value of Kc at a given temperature. If you increase that temperature, that changes the value of Kc for that reaction, okay, or decrease the temperature. Secondly, all substances when we're studying Kc have to be in the same state. So we're not going to deal with anything solid or pure liquids for our case. Yes, you can establish and study equilibriums involving multiple states, but for our purposes, we're just going to look at when we're dealing with all aqueous solutions, so when we're dealing with concentrations, or all gases. And three, a very important thing is that the equilibrium constant does not tell us any information about the rate of the reaction. Okay, only the concentrations once the reaction is at equilibrium. The equilibrium, perhaps we have an equilibrium where we have a lot of products. Products are on the top over here in our equilibrium expression. Okay, so perhaps we have a very large Kc. Let's say we have a Kc of like 10 to the 10, which means a lot of products are present. Okay, but that doesn't tell us how fast those products are formed. This could take a year in order to form that amount of products and actually establish the equilibrium. Okay, it just tells us how much at equilibrium, so there's no information about how fast that it reaches equilibrium. So what does Kc mean? Okay, so our generic reaction again, we have our Kc is the concentration of products over our concentration of reactants. So when you're writing it, again, the products go on top. Okay, and you raise them to the coefficients and they are multiplied by each other. Okay, in the bottom we have A, and B, B. So it's important that you raise each to its coefficient in the equation, and it's also important you do not add or subtract the different values. Everything is being multiplied. So let's take a look. What does Kc mean? So if the concentration of products and reactants are the same, we will get a value of Kc equal to 1. Okay, in that case, when Kc is equal to 1, the equilibrium, everything is equal, and the concentration of reactants is equal to the concentration of products in this case. Okay, so they're both the same amount. Now, as we studied with equilibrium, the concentrations remain constant, but they do not have to be equal. In the case where Kc is 1, they are, though. Okay, so what happens when Kc is smaller than 1? So perhaps we have a Kc of 0.01. Okay, when this happens, so if we look again, this means that the reactants, our denominator of our fraction, must be larger than our products in order to get a Kc of 1. So the bottom of the fraction has to be bigger. Since the reactants are larger, in this case we say that the equilibrium lies to the left. Okay, that's saying that the equilibrium is predominantly on the reactant side, and the concentration of reactants is greater than the concentration of products present at equilibrium. If Kc is larger, so let's say we have a Kc of 100, it's the exact opposite. So since we have a large Kc, this means the top of our fraction or our products, which I just realized that I spelled wrong, P-R-O-D-U-C-T-S, there we go, products, has to be larger. So we say that the equilibrium lies to the right, or it lies to the product side, which is on the right-hand side of our equation. And we have that the concentration of reactants is smaller than the concentration of products. Now, what happens if Kc gets really, really small or really, really large? So in this case, let's say that Kc is smaller than 10 to the negative 10. Okay, when this happens, so Kc is so small. So imagine the size. The reactants compared to products would have to be quite a lot larger than the amount of products. So we say almost no reaction. So almost no reaction occurs in this case. Okay, and we have mainly all reactants present. Very, very few products would be present at equilibrium because it doesn't really go forward with this equilibrium. Whereas when we have a very large Kc, so let's say Kc is greater than 10 to the positive 10, okay, we generally say that the reaction goes to completion. Okay, so the reaction essentially goes to completion, and at equilibrium, we have all products. So we assume that would be more like, it is technically still equilibrium, but more like a regular reaction where everything just goes right to the product side. Okay, so quick example. Consider the reaction of hydrogen and iodine to produce hydrogen iodide. So H2 plus I2, it's an equilibrium reaction with 2HI. Calculate the Kc given the concentrations at equilibrium are as follows. Okay, so first we have to establish our equilibrium constant expression. So Kc, which is the products, Hi raised to their coefficient. So Hi squared divided by H2 times I2. So everything is multiplied and everything is in square brackets because we're dealing with concentrations. Okay, then it's just a matter of filling in our values. So for Hi, we have 0.028 squared on the top over 0.0037 times 0.0037. And that gives us a value of 57.3. Now, another thing you'll notice with Kc is on the top, we have units of mole per decimeter cubed, and on the bottom we have mole per decimeter cubed. So we actually, with our Kc, it's unitless. So our Kc will always be unitless. We don't express any units. It's just a number, and that number again is just telling us a ratio of how many products we have to how many reactants. So in this case, it's saying at the equilibrium, given the Kc is larger than 1, that we have mainly products in our equilibrium reaction, but we would still have a measurable amount of reactants as well. Kc can also be manipulated. Okay, so we can look at Kc. If we take a reaction and say reverse the reaction or double or triple the reaction, or maybe we have a multi-step reaction, how do we deal with Kc? So this is a summary table, but we're going to take a look at a breakdown of a question in a second. So for example, if we invert the reaction, so if we flip it around, okay, it inverts our equilibrium expression, which flips Kc on its head, and we'll see this in a moment. If we doubled everything in the reaction, we end up getting a value of Kc squared, so the original one squared. If we half it, it would be Kc to the 1/2, which would be the square root of Kc. Or in the case if we have a multi-step reaction, so if we have two reactions or something that takes place in two separate steps, we would multiply the two Kc expressions together to get our overall Kc value. Okay, so let's take a look. It'll make a little more sense when we actually see an equation. But if you want to copy this summary table, it would be a good idea. Okay, so here we have the equilibrium constant for the reaction, 2Hi, in equilibrium with H2 and I2, is 0.040 at 298 Kelvin. What would the value of Kc be for the following reaction at the same temperature? Okay, so we've established our initial, let's take a look. Let's write our initial Kc. Kc is equal to 0.040, and our Kc expression for the original reaction is going to be H2 times I2, since those are our products, over Hi squared. So let's see what's happening in this new reaction. So it's similar to our original, but we've flipped the reaction. Okay, so we've spun it around backwards, and also we have multiplied the reaction by 1/2. So we've divided everything by 2. So how is this going to affect our Kc? So let's do it for just the flipping of the reaction first. I'm going to call this Kc prime, which is just flipping. Let's see what happens. Let's write it down. So Kc prime, when we flip the reaction, before we divide it by 2, we would get the equilibrium expression, Hi2 over H2 and I2. So we can see that it's our original expression, but flipped upside down, which means that if we flip the equilibrium expression, what happens to our Kc is we can calculate our new Kc by taking 1 over the original. Okay, so so again, we've inverted, we flipped the reaction, which inverts our equilibrium expression. So for our new Kc, it's equal to 1 over our original Kc. Now the second step we did was we divided everything by 2. So cutting everything in half, let's just call this K double prime for a second. So K double prime is going to be our divided by 2 and our flipped around. So we would have Hi. So if we divided it by 2, its exponent would just become 1. Divided by H2 to the 1/2 times I2 to the 1/2. So the equivalent of dividing our reaction by 2, what's happened in our equilibrium expression is it's actually the square root, right, of our expression. So we've taken the square root. So our K would become 1 over the square root of our original equilibrium expression if we flipped it and multiplied by 1/2. Okay, so now we can actually calculate it. Now that we know our final K, is equal to 1 over the square root of Kc. We have our original Kc, so 1 over the square root of 0.04. And that gives us an answer for our new Kc of our new reaction of 5. Okay, and that brings us to the end of our discussion on Kc. So remember, a few important facts about it is that the equilibrium constant is specific for a given reaction at a given temperature. It is unitless. Okay, a larger Kc means that we have mainly products. A Kc of 1 means that we have an equal amount of products and reactants, and a Kc of less than 1 means that we have mainly reactants when we are at equilibrium. And we can manipulate our Kc by manipulating our initial reaction. Oh, and Kc does not tell us about the rate of the reaction, again, only about how much substance is present at equilibrium, not how fast it reaches equilibrium.